Right now, wherever you are, you feel still. The floor holds steady, nothing seems to move, and yet you are being carried. The Earth turns and circles the Sun, and the Sun itself is falling through the galaxy, pulling all of us along at well over 500,000 miles an hour. We're always going somewhere. Tonight, the somewhere matters. Our Sun is drifting through a thin veil of gas and dust between the stars, a wisp astronomers call the Local Interstellar Cloud. We slipped into it tens of thousands of years ago, and within a few thousand more we will leave it again for another cloud beyond. Far past the edge of everything the planets know, the solar wind meets that veil and builds a fragile shield around us. What waits in that region, and what happens as we move deeper into it, is something scientists are only beginning to understand. So let us go and look, slowly, all the way out. Sit still for a moment and notice how solid the world feels. The floor does not shift. Your cup of tea rests where you left it. Everything around you agrees that you are not moving, and all of it is wrong. You're moving faster right now than you ever will in any car or plane, faster than you can really imagine, and you feel none of it. Start small. The Earth turns beneath you, carrying you eastward. At the middle of the planet, that spin runs at about 1,000 miles an hour. On top of that, the Earth swings around the Sun, a far larger loop, and along that path we travel near 67,000 miles an hour. That is the speed that keeps us from falling into the Sun, and it never lets up. But the Sun is not standing still either. Hold that thought, because it is the one that matters tonight. The Sun, with the Earth and every other planet tucked around it, is falling in a great circle around the centre of the galaxy. It moves at something over 500,000 miles an hour. At that pace, it still takes the Sun somewhere between 200 and 250 million years to finish a single lap of the Milky Way. The last time the Sun was in the spot it occupies now, there were no flowers on Earth, and the dinosaurs had not yet appeared. Picture it plainly. We sit about 26,000 light-years out from the bright, crowded core of the galaxy, far out in the calmer suburbs. From there, the whole solar system is being swept along a slow, enormous arc, like a single boat carried by a current so wide you cannot see its banks. You are on that boat, so is everyone you have ever known. Here is the strange and gentle truth of it. Because everything near you moves together, you feel nothing. The Sun pulls the planets pull their moons, and the whole arrangement drifts as one. There is no wind in your face, no sense of speed, no landmark close enough to rush past. It is the same reason a passenger asleep on a smooth night flight does not feel the hundreds of miles an hour outside the window. Steady motion, shared by everything around you, simply disappears. And yet the journey is real, and the scenery does change. The space between the stars is not empty. It is thin, far thinner than the best vacuum we can make in a laboratory, but it is not nothing. It has gas in it, and dust, and faint magnetic fields, and it comes in patches. Some regions are a little warmer, some a little denser, some carry the scattered ash of stars that died long ago. As the Sun drifts along its great arc, it passes from one of these regions into the next, the way a ship passes from open water into a bank of fog and out again. We are passing through one of those regions now. We have been inside it for tens of thousands of years, and we will leave it within a few thousand more. What it is made of, and what it does to us as we move through it, is the whole of our story. So the first thing to hold on to is simply this: you are not still. You are travelling right now through a particular stretch of the galaxy, and to understand where we are, we first need to know which way we are going. Every traveller has a direction, even one who feels no motion. The Sun has one too. There is a single point on the sky toward which our whole solar system is steadily heading, the way the front of a ship points into the water ahead. Astronomers gave it a quiet name. They call it the solar apex. You can find it on a clear night, if you know where to look. The solar apex sits in the constellation Hercules, near its border with the bright little constellation Lyra, not far from the brilliant star Vega. When you face that part of the sky, you're looking straight out the front windshield of the solar system. Everything ahead of us, every wisp of gas and grain of dust in that direction, is space we're about to move into. Turn around, toward the opposite point, and you're looking out the back window at the space we have already left behind. How fast are we going through this nearby crowd of stars? Slower than the great galactic arc, because here we measure our motion against our neighbours rather than against the distant core. Relative to the average drift of the stars around us, the Sun moves at roughly 12 miles every second. That is a gentle pace by the standards of the last chapter, but it is still about 43,000 miles an hour, and it is steady, and it never stops. There is a second speed worth holding, and it is the one that will matter most. The thin gas between the stars is itself drifting, and it does not drift with us. So if you stand on the Sun and ask how fast the surrounding interstellar gas is flowing past you, the answer is a little higher, around 16 miles a second, near 26 kilometers a second in the units the scientists use. To us, riding along inside the solar system, it feels less like we are moving, and more like a faint, endless wind is blowing toward us out of the direction of the solar apex. A wind of single atoms, mostly hydrogen and helium, streaming past at 16 miles every second. Think of standing in a slow river. The water moves, and you feel it press against your legs from upstream. The Sun feels something like that, a soft pressure of interstellar gas coming from ahead. And just as a river tells you which way is downstream, that flow of atoms tells us, from inside the solar system, exactly which way we are headed and how the space around us is arranged. This matters for a simple reason. If we are moving in a definite direction, then we are always arriving somewhere new. The patch of galaxy in front of us is not the same as the patch behind us. The gas thickens and thins. The Sun does not sit in a fixed room. It walks slowly down a long hallway, and the hallway keeps changing. So we know our speed, and we know our heading. We are aimed at Hercules, sliding forward at 12 miles a second through our corner of the galaxy, with a faint wind of stardust blowing steadily into our face. The next question is the one that protects us, because before any of that interstellar wind can reach the Earth, it has to get past a vast invisible shield the Sun builds around all of us. That shield is where we go next. The Earth is not naked to the galaxy. Between us and that faint interstellar wind there is a shelter, enormous and invisible, blown by the Sun itself. It surrounds every planet, reaches far beyond the most distant of them, and we live our entire lives deep inside it without ever seeing it. Scientists call it the heliosphere, which simply means the sphere of the Sun. Think of it as a bubble, not a soap bubble, thin and fragile, but a vast region of space that the Sun has cleared out and claimed as its own. Inside this bubble, the Sun is in charge. Its particles, its magnetic field, and its influence fill the space. Outside the bubble lies the rest of the galaxy, the true interstellar medium, governed by other stars and older forces. The heliosphere is the line between what belongs to the Sun and what does not. It is hard to overstate how large this shelter is. Pluto, far out at the cold edge of the planets, orbits at about 40 times the distance from the Earth to the Sun. The wall of the heliosphere lies roughly 3 times farther still, past 120 times the Earth-Sun distance in the direction we are heading. If you shrank the Earth's orbit down to the size of a coin on a table, the edge of the heliosphere would be a fence more than 10 feet away. Everything we have ever touched, every planet, every moon, every comet we have named, sits well inside that fence. The shape is not a neat round ball, though we call it a bubble out of habit. Because the Sun is moving, and because that interstellar wind is always pressing against the front, the heliosphere is squashed on the leading side and drawn out into a long tail behind like the wake of a boat. One leading team, after years of computer modelling, argued the whole thing looks less like a sphere and more like a soft, deflated croissant, with 2 great lobes trailing away. The exact shape is still argued over, which tells you how much remains to be learned about something so close to home. What does the bubble do for us? it shields. The galaxy is full of fast, dangerous particles called cosmic rays, the shrapnel of distant exploded stars, racing through space at nearly the speed of light. Many of them come from far beyond our shelter. When they reach the heliosphere, most are turned aside or slowed by the sun's outflowing material and tangled magnetic field. Only a fraction make it through to the inner planets. The bubble is, in a real sense, the first layer of protection that allows the delicate chemistry of life on Earth to carry on undisturbed. So we have a shelter, and we have a wind pressing on it from outside. That sets up the central tension of everything that follows. The strength of the shelter depends on how hard the sun pushes out, and on how hard the surroundings push in. As long as the push from the sun is strong and the surroundings are thin, the bubble stays large and Earth stays deep inside it, well protected. But the surroundings are not always thin. As we will see, the sun has wandered into denser regions before, and the bubble has been squeezed hard. To understand how the shelter could ever shrink, we first need to understand what holds it up. The heliosphere is inflated like a balloon by a constant breath from the sun. That breath has a name, and it is where we turn next. The sun is not a quiet ball of fire. It leaks. From its outer atmosphere, a thin, scorching stream of charged particles flows outward in every direction, never stopping, never running dry. This is the solar wind, and it is the breath that keeps the heliosphere inflated. Without it, the shelter around us would collapse. The solar wind is made of plasma, which is simply gas so hot that its atoms have been torn apart into pieces. Picture ordinary gas, then heat it until the electrons are stripped away from the atoms, leaving a soup of free particles that respond to magnetic fields. That is plasma, and most of the visible universe is made of it. The sun's outer layer, the corona, is hot enough, well over 1 million degrees, that it cannot hold itself together. It boils off into space. The speed of this wind is hard to believe from the ground. On a calm day, it streams past the Earth at around 1 million miles an hour. When the sun is restless, gusts can run nearly twice that fast, yet the wind is so thin that we never feel it. By the time it reaches us, there are only a handful of its particles in a space the size of a thimble. It is a hurricane made of almost nothing, blowing forever. Here is the part that matters for our shelter. The solar wind does not just drift away and vanish. It carries the sun's outward pressure with it, pushing against the surrounding galaxy. As long as that push is strong, it holds the interstellar wind at bay and keeps a clear bubble swept out around us. The heliosphere is, quite literally, the region the solar wind can reach before it is finally stopped. And it is stopped by a balance, the same kind of balance you can see in any standoff between two streams of water. Imagine turning a garden hose onto a slow-moving river. Near the nozzle, the water you spray pushes the river back and clears a little space. Farther out, the river pushes back harder, until at some distance the two forces meet, and neither gains ground. That meeting line is where your influence ends. The heliosphere works the same way. The solar wind pushes out, the interstellar gas pushes in, and the wall of the bubble forms exactly where the two pressures match. This tells us something quietly important. The size of our shelter is not fixed. It is a negotiation. If the sun blows harder, the bubble grows. If the surrounding gas grows thicker and presses in harder, the bubble shrinks. For most of recorded human history, the surroundings have been thin. The wind has held and the bubble has stayed enormous. But the strength of the wall depends entirely on what the sun is pushing against, and that, as we'll see, can change. The solar wind weakens with distance, the way any spray loses its force the farther it travels. Out past all the planets, in the cold dark beyond Pluto, it finally runs out of strength. It slows, it piles up, and it meets the wall it has built. That outer region, where the sun's breath gives way to the galaxy, is not a single sharp line. It is a layered border with several distinct zones, each with its own name and its own behaviour. To leave the solar system, you must pass through all of them. 2 machines built by human hands have done exactly that, and the story of those edges is where we go next. Leaving the heliosphere is not like stepping through a doorway. There is no single wall, no clean line where the sun's world stops and the galaxy begins. Instead, there are layers, a series of edges stacked one beyond the next, each marking a different stage in the long defeat of the solar wind. To truly get outside, you have to cross all of them. There are 3 that matter most. The first edge is called the termination shock. Out beyond the planets, the solar wind has been racing outward for years, faster than the speed at which a disturbance can travel through the surrounding gas. Then, all at once, it slams into the resisting pressure of the galaxy and is forced to slow down, dropping below that speed in an abrupt jolt. That sudden braking is the termination shock. In today's heliosphere, it sits somewhere around 85 to 94 times the Earth-Sun distance from us. Think of a fast river meeting a deep, still lake. Where the rushing water suddenly piles up and slows, the surface jumps. That jump is the shock. Past that, the wind does not simply stop. It enters a thick, turbulent zone called the heliosheath, where the slowed solar wind churns and folds back on itself, building up against the boundary ahead. This is the crowded outer shell of our bubble, a region of hot, sluggish, tangled plasma. If the clear inner heliosphere is the calm body of the lake, the heliosheath is the choppy, piled-up water near the shore, where everything is dense and confused. The third edge is the real border. It is called the heliopause, and it is the true skin of the bubble, the place where the sun's material finally gives way to the gas of interstellar space. Inside the heliopause, the particles around you came from the sun. Outside it, they came from the galaxy. Cross that line, and you have left the sun's domain entirely, even though the sun still shines bright behind you as the brightest star in your sky. The heliopause in our direction of travel lies a little past 120 times the Earth-Sun distance away. It helps to put that number against something human. Light, the fastest thing there is, takes about 8 minutes to travel from the sun to the Earth. To reach the heliopause, that same light needs almost a full day. A signal sent from the edge of our bubble takes the better part of a day just to reach us, travelling at the only speed nothing can beat. That is how far out the wall stands. These 3 edges are not still. They breathe in and out as the sun grows more or less active, swelling when the solar wind is strong and drawing inward when it weakens. They also shift depending on how hard the galaxy is pushing back. On the side facing our direction of travel, they are pressed close. On the trailing side, they stretch far into the long tail of the bubble. The whole structure is alive, flexing slowly against the pressures around it. For a long time, these edges were only ideas, drawn on diagrams, their distances guessed at from models. No one had ever been there. We knew the shelter had a wall, but we had never touched it, never measured the moment of crossing, never felt the galaxy on the far side. Then, after a journey of more than 30 years, 2 small spacecraft launched in the 1970s reached those edges one after another and sent word back across the dark. They are the only human-made things ever to leave the bubble, and what they found is where we turn next. In the late summer of 1977, 2 spacecraft left Earth within weeks of each other. They were called Voyager 1 and Voyager 2, and they were built to tour the outer planets, to fly past Jupiter and Saturn and beyond, and send home the first close portraits of those distant worlds. They did all of that. But their real legend came much later, long after the planets were behind them, when they did something no machine had ever done. They flew off the edge of the map. Voyager 1 reached the wall first. For years, its instruments had been counting the particles around it, watching the solar wind thin and slow as it climbed toward the boundary. Then, on the 25th of August in the year 2012, everything changed at once. The count of low-energy particles from the sun fell away sharply, and the count of high-energy cosmic rays from the galaxy jumped up. The plasma around the spacecraft grew suddenly denser, the signature of interstellar gas rather than solar wind. Voyager 1 had crossed the heliopause. It had left the bubble. after 35 years of flight, a craft built by human hands was for the first time in interstellar space. It had travelled about 121 times the distance from the Earth to the Sun to get there. By then, its radio signals, crossing that gulf at the speed of light, took the better part of a day to reach us, growing fainter every year as the spacecraft pushed farther out. Voyager 2 followed, taking a different road. It was aimed at another part of the sky, and it moved a little slower, so its crossing came years later. In November of 2018, more than 6 years after its twin, Voyager 2 passed through its own stretch of the heliopause, at about 119 times the Earth-Sun distance. Its instruments told the same story in their own way. The solar wind around it dropped off and never returned, while the markers of interstellar space rose to take its place. Now there were 2 crossings, in 2 directions, made by 2 machines, and they agreed. The wall was real, and we had measured it twice. Edward Stone, the long-serving scientist who guided the Voyager mission for decades, had waited much of his career for this. He and his colleagues had drawn these edges on paper long before anyone could visit them. To watch the data confirm the crossing, live, from a craft already beyond the sun's reach, was the payoff of a lifetime of patience. What the Voyagers found was not a clean, calm frontier. The boundary turned out to be more tangled and surprising than the simple diagram suggested. The magnetic field on the far side did not point quite where models predicted. The transition came in fits and layers rather than a single neat step. Even now, with both craft well past the heliopause, scientists argue about how much of what the Voyagers feel is truly the open galaxy, and how much is still the distorted edge of our own bubble, bending the interstellar field around itself like a stone in a stream. That uncertainty is the honest state of things. We have 2 priceless witnesses sending back whispers from beyond the wall, and they have already rewritten what we thought we knew. But 2 points, in 2 directions, can only tell us so much about a region that surrounds us on every side. So what does lie just outside the wall? The Voyagers have given us our first real taste of it. That faint surrounding sea is where we go next. Once you cross the heliopause, you are in a new country. It has a plain and careful name, the very local interstellar medium, meaning the particular patch of between the stars material lying just outside our bubble, in our immediate neighbourhood. It is the first thing the Voyagers met on the far side of the wall, and it is the first real piece of the galaxy our instruments have ever touched directly. It is important to be honest about how empty it is. Out here, the gas is thinner than anything we would call a vacuum on Earth, where the air you are breathing has more particles in a single breath than there are stars in the galaxy. The very local interstellar medium holds only a few tenths of an atom in a space the size of a sugar cube. If you scooped up a cube of it the size of your fist, you might catch a handful of atoms, and that would be a crowded sample. By any human measure, it is almost perfectly empty. And yet it is not nothing, and that almost is the whole point. Across the immense distances between stars, those few thin atoms add up. They carry pressure. They carry a faint magnetic field. They are pushing back against our shelter from the outside, and they are the very thing whose pressure decides how big our bubble can be. Thin as it is, this is the sea our boat sails through, and the sea sets the rules. The Voyagers, drifting now in this region, have measured it in ways no telescope could. They feel the density of the surrounding plasma rise and fall. They feel the local magnetic field draped and bent around the outside of the heliosphere like a rubber band stretched over a beach ball. They have even recorded faint ringing vibrations passing through the interstellar gas, a kind of distant hum, the medium itself trembling when a gust of solar activity races out from the sun and shakes it. For the first time, we are not guessing about the space beyond the wall, we are listening to it. One scientist described this material in a way worth keeping. It is, she said, a relic of the environment the solar system was born out of. The gas between the stars is the leftover stuff of star formation, the same kind of raw material from which the sun and earth condensed billions of years ago. To sample it now is to touch, faintly, the ingredients of our own origin, and to glimpse the conditions in which other stars are still being made. But here is the catch that keeps the scientists cautious. Even the Voyagers, brave as they are, have not reached truly pristine, undisturbed interstellar space. They are still close enough to the heliopause that our own bubble warps the gas and the magnetic field around them. The medium they feel is the galaxy seen through the distorted glass of our shelter's outer edge. The clean, untouched interstellar field lies farther out still, in a region no craft has yet entered. So we have crossed the wall and we have dipped a toe into the sea beyond it. We know it is thin, magnetic, and alive with faint motion. But the very local interstellar medium is not uniform. It is not one smooth ocean. It comes in patches, in clouds, in regions of slightly different density and temperature drifting against one another. And the sun right now is sitting inside one particular cloud. That cloud is the region this whole story is named for. It is time to step into it. The sun does not float in plain, even emptiness. Right now, today, it sits inside a specific cloud, a thin and ragged wisp of interstellar gas with a shape and an edge and a name. Astronomers call it the Local Interstellar Cloud. They also have an older, friendlier name for it that has stuck, because it captures how flimsy the thing is. They call it the local fluff. Do not picture a cloud the way you would in the sky, white and billowing and clearly bounded. This cloud is so thin it would be invisible if you stood inside it, which you do since we all live within it. It is a faint thickening of the interstellar medium, a region where the gas is a little less empty than the void around it. But it is real. It is enormous, and we have measured it. In size, the Local Interstellar Cloud stretches roughly 30 light-years across. That is a span so large that light, crossing it at the only unbeatable speed, takes 30 years to make the trip. The sun is somewhere inside this wisp, drifting through it the way a small boat drifts through a long, slow patch of fog. Everything we see in the night sky that is closer than 30 light-years sits inside this same cloud with us. Now the curious part, the kind of fact that stops you. The Local Interstellar Cloud is hot. Its temperature runs around 7,000 degrees, close to the temperature of the visible surface of the sun itself. And yet, it could never burn you, never even warm you. Because heat is not only about temperature, it is also about how much stuff there is to carry that heat. This cloud is so thin, with only about 3/10 of an atom in a space the size of a sugar cube, that there is almost nothing there to pass warmth along. A single spark is searingly hot, but it cannot heat a room. The local fluff is a cloud of searing sparks spread so far apart that, to us, it is colder than empty space feels and quieter than silence. How do we know we are inside it, rather than merely near it? Because we can feel its wind. The faint stream of interstellar atoms blowing through the solar system, the same wind we met earlier coming from the direction of the solar apex, carries the fingerprint of this particular cloud. By measuring the speed and direction of that flow, scientists have matched it to the motion of the Local Interstellar Cloud. The wind in our face is the breath of the fluff, and that tells us the sun is presently embedded in it. We did not arrive here long ago. The best estimates say the solar system entered the Local Interstellar Cloud sometime within the last tens of thousands of years. The exact figure is uncertain, with reasonable guesses ranging from around 40,000 to over 100,000 years ago. To put that in human terms, our distant ancestors were already walking the earth, already making tools and fire and art, when the sun first slipped into this cloud. The whole of recorded history, every empire and every story ever written, has happened inside the local fluff. So this is our address, the small room of the galaxy we currently occupy. A thin, hot, ragged wisp of gas 30 light-years wide, which we entered while humans were still painting caves, and which we will leave again before too long. But knowing we are inside it raises a sharper question. How exactly do we measure something so faint, something we cannot see and can barely touch? The answer is one of the quiet triumphs of modern science, and it is where we go next. How do you measure a cloud you cannot see, made of gas so thin it is barely there, surrounding you on every side? You cannot photograph the local interstellar cloud. You cannot fly to its edge and look back. It is 30 light-years across. The clever answer is that you do not study the cloud from outside. You let a little piece of it come to you, and you taste the wind. Remember the steady flow of interstellar atoms blowing through the solar system from the direction of the solar apex. Most of those atoms are electrically charged, and the sun's magnetic shelter turns them away at the wall, never letting them in. But not all of them. Some of the atoms in the cloud are neutral, carrying no charge at all, and a magnetic field has no grip on something with no charge. Those neutral atoms sail straight through the heliopause as if the wall were not there, drifting deep into the solar system, all the way past the planets. Helium is the perfect spy for this. Helium atoms in the interstellar gas are mostly neutral, and they are sturdy, so they survive the long journey inward. They stream through our bubble in a thin, steady current, and spacecraft can catch them. By measuring the direction that current comes from and how fast it is moving, scientists can read off the speed and heading of the cloud outside, like feeling which way a breeze blows by holding up a wet finger. This is exactly how the flow was pinned down. A craft named Ulysses, which flew over the poles of the sun in the 1990s, sampled this incoming helium and measured its motion. Years later, a dedicated mission did it again with far greater precision. The numbers told a clear story. The interstellar gas blows past the sun at about 16 miles a second, coming from a specific point on the sky, and its properties matched the local interstellar cloud. The wind of atoms confirmed where we live. There is a second way to taste the cloud, and it reaches farther. When astronomers look at a nearby star through the thin interstellar gas, the gas leaves a mark on the starlight. Atoms of certain elements absorb very specific colours, punching narrow dark gaps into the star's spectrum like a fingerprint pressed onto the light. By reading those gaps, scientists can tell what gas lies between us and that star, how dense it is, how warm it is, and how fast it is moving. Each nearby star becomes a probe, and the dark lines in its light become a sounding of the cloud along that line of sight. Piece together enough of these soundings toward enough different stars, and a rough map begins to form. This is how we learned that the local interstellar cloud is not perfectly smooth, that its edge is irregular, and that other clouds lie nearby in other directions. It is painstaking work, reading whispers in starlight and faint currents of helium, and it leaves much still uncertain. But it is real measurement, not guesswork, and from it the shape of our neighbourhood slowly emerges. There is one more piece of evidence, and it is the most beautiful of them. When the incoming interstellar atoms interact with the edge of our bubble, they sometimes get flung back out as fast, neutral particles, glowing faintly across the whole sky in a pattern. One spacecraft was built to map exactly that glow, and what it found surprised everyone. It saw a great arc written across the heavens, a structure no one had predicted, and it remains one of the strangest sights in all of nearby space. That arc has a name. It is called the Ribbon, and it is where we go next. In October of the year 2008, a small spacecraft slipped into orbit around the Earth with a single, focused job. Its name was the Interstellar Boundary Explorer, though almost everyone shortened it to its initials. It carried no camera for ordinary light. Instead, it was built to map something invisible, the faint glow of fast, neutral atoms streaming back inward from the distant wall of our bubble, where the solar wind wrestles with the surrounding cloud. By gathering those atoms from every direction, it could build, slowly, an all-sky picture of the edge of the heliosphere, a place far too distant to photograph any other way. When the first full map came together in 2009, it held a shock. Splashed across the sky was a bright, narrow arc, a long curving band of stronger emission where the atoms streamed back more thickly than anywhere else. Nothing in the existing models had predicted it. The scientists, led by the mission's head, David McComas, were genuinely caught off guard. They gave the feature the plainest possible name, They called it the ribbon. The ribbon is not a thing you could fly to and touch. It is a pattern in where these returning atoms come from, a region of the sky where the boundary of our bubble glows brighter. But its very existence said something important. The edge of the heliosphere is not smooth and featureless. Something is organising it, focusing it, drawing a great arc across the heavens. The question was what? The leading answer points to magnetism. The local interstellar cloud carries its own faint magnetic field, far weaker than the Earth's, drifting through the gas. As that field presses against the outside of our bubble, it drapes around it, the way a stream bends around a stone. Along one particular curving line, the geometry works out just so, and the returning atoms pile up there more than elsewhere. If that picture is right, then the ribbon is a kind of shadow of the local interstellar magnetic field, written across the sky by the way it wraps our shelter. By studying the arc, scientists can read the strength and direction of a magnetic field they could never measure directly, a field only a few millionths as strong as a refrigerator magnet, yet large enough to shape the wall of our world. Here is the detail that ties this back to our two distant travellers. The ribbon curves through a stretch of sky that lies between the paths of Voyager 1 and Voyager 2. Neither spacecraft flew through it. As one scientist put it, it was like having two weather stations on the ground and missing the great storm that passed between them. The Voyagers gave us the texture of the boundary up close, in two narrow spots. The ribbon gave us its grand shape across the whole sky. Each filled in what the other could not reach, and together they began to confirm the same answer about which way the local magnetic field points. And yet the ribbon remains, in honest words, only partly understood. We have a leading explanation, supported by the Voyager measurements and by other craft, but the fine details of how it forms are still argued over. It is one more reminder that the space just outside our door, which sounds like it should be simple and empty, keeps surprising the people who study it most closely. The ribbon told us about the magnetic skin of our bubble, but it also reminded us that the cloud we live in has a shape and an edge, and the sun, it turns out, is not sitting comfortably in the middle of that cloud. We're near the way out. We're not deep inside the local interstellar cloud. We're near its edge, standing close to the door on our way out. That single fact changes how this whole story feels. We did not settle into the middle of a great hot wisp to stay. We're passing through it, and the far side is not far off. The measurements that tell us this are the same ones we have been gathering all along. The wind of helium atoms, the dark fingerprints in starlight, the slow mapping of the cloud's irregular shape. Put them together, and the sun comes out sitting near the boundary of the local fluff, with the cloud thinning out ahead of us in the direction we're travelling. We're closer to the exit than to the heart. How soon do we leave? Here the honest answer is a range rather than a date, because the edges of these clouds are ragged and our map is rough. Some careful analyses put our remaining time inside the cloud at no more than about 1900 years. Others stretch it to a few thousand. Either way, by the long clock of the galaxy, it is the blink of an eye. The sun has lived more than 4.5 billion years. To say we will leave this cloud within a few thousand years is like saying a person who has lived their whole life will step out of one particular room sometime in the next few seconds. Look back the other way, and the picture matches. We entered this cloud only tens of thousands of years ago, sometime in the rough window between 40,000 and over 100,000 years past. So our entire stay in the local interstellar cloud from entrance to exit spans something like 100,000 years at most. The cloud is a brief chapter, not the whole book. Modern humans had already spread across the Earth before we arrived, and our distant descendants, if there are any, may still be here to see us leave. It is worth sitting with how strange this is. Every sunrise you have ever seen, every season, every harvest in all of human history has happened during this one short passage through one thin cloud. The cloud has been the unchanging backdrop of everything we have ever done, and it has been there the whole time without anyone before our own era even suspecting it existed. And it is temporary. We are tenants near the end of a lease, with the door already in view. This raises the obvious next question, the one a child would ask. If we're about to leave this room, what room comes next? When the Sun finally crosses out of the local interstellar cloud, what does it cross into? The answer is not simple emptiness. Just beyond our cloud, in the direction we are heading, lies another. There is a second wisp of interstellar gas pressed up close against ours, possibly already touching it, and the Sun appears to be aimed more or less toward it. It is a different cloud, with a different temperature and a different character, and it has one feature that makes it impossible to ignore. It holds, within it, the closest stars to our own. The next cloud has a name, the G cloud, and it is where we turn next. When the Sun finally drifts out of the local interstellar cloud, it will not step into clean, open space. Pressed close against the far side of our cloud, in roughly the direction we are heading, lies another wisp of interstellar gas. Astronomers call it the G cloud. It is the next room down the hallway, and it has a feature that makes it feel oddly personal. The G cloud is where our nearest neighbours live. The closest star system to the Sun, Alpha Centauri, sits embedded within the G cloud, just over 4 light-years away. When you look up at that famous point of light, low in southern skies, you are looking not only at the nearest stars but at the cloud they float in, the very cloud the Sun is drifting toward. Our closest stellar neighbours and our next galactic environment are, it turns out, the same place. The G cloud is similar to our own in many ways, another thin, warm wisp of partly broken up gas, but it is not identical. The measurements we have, gathered from the dark fingerprints in the starlight of Alpha Centauri and of a star called 36 Ophiuchi, suggest the G cloud is a touch cooler than the local fluff. Where our cloud runs near 7,000 degrees, the G cloud reads closer to 5,900. There are also hints that it may be somewhat denser, with more atoms packed into each stretch of space. If that is right, it carries a quiet significance, because a denser cloud presses harder on our shelter, and a harder press means a smaller bubble. But honesty matters here, and the honesty is humbling. Our entire knowledge of the G cloud rests on just a couple of lines of sight, a mere handful of stars whose light happens to pass through it on its way to us. With so few probes, the cloud's true shape, density, and extent remain genuinely uncertain. We are describing a place we've glimpsed only at the edges, through 2 narrow windows, and we should hold our conclusions loosely. When will we reach it? As with our exit from the current cloud, the answer is a range, not a date. Some estimates suggest the Sun could enter the G cloud within a few thousand years, soon after leaving the local fluff. Others stretch the crossing tens of thousands of years into the future. There is even a real possibility that the 2 clouds are already touching, their ragged edges overlapping somewhere ahead of us, so that our passage from one to the other will be gradual rather than sharp, a slow fading from one room into the next, with no clear threshold between them. And there is a further wrinkle, the kind that keeps this subject so unsettled. It is not certain that the G cloud is even the next cloud we will meet. Other small wisps of gas drift in the space ahead, closer to us than the G cloud in some directions, and one of them might reach us first. The map of what lies in front of the Sun is genuinely contested, with reasonable scientists drawing it different ways. This is the heart of why our title says nobody understands this region. We can name the clouds, we can measure a few of their properties, but the boundaries between them and the order in which we will pass through them remain blurred. To see why, we need to look at the cluster of smaller cloudlets crowding the space just ahead of us, and at one in particular that sits right in our path. The picture of 2 tidy clouds, ours and the G cloud, lined up neatly one behind the other, is too simple. The real neighbourhood is messier than that, and the mess is the truth. The space around the Sun is not divided into a few clean rooms. It is a patchwork of small drifting wisps, each with its own speed and direction, crowded together and overlapping at their edges. Scientists call these smaller pieces cloudlets, and there are something like 15 of them identified within a few dozen light-years of us. Each cloudlet was found the same patient way, by reading the dark fingerprints that interstellar gas leaves in the light of nearby stars, and by noticing that the gas in different directions moves at slightly different speeds. A wisp drifting one way leaves its mark shifted just so. A wisp drifting another way shifts the starlight differently. By sorting these subtle differences, astronomers have teased apart the local gas into separate clouds, like distinguishing the voices in a quiet, overlapping conversation. One cloudlet matters more than the others for our story, because it sits almost directly in our path. The astronomer Priscilla Frisch, who has spent a career mapping this nearby gas, identified a wisp lying within about 16 light-years of the Sun, right in the direction we are travelling, the direction of the solar apex. Because it sits at our apex, the leading point of our motion, she called it the apex cloud. If it is real and solid, it could be among the first new environments the Sun encounters as it leaves the local fluff, possibly even before the G-cloud. That little phrase, if it is real and solid, is doing a great deal of work, and it should. These cloudlets are faint, their edges uncertain, their existence sometimes resting on a single sightline. The apex cloud shows up clearly towards some stars and barely at all toward others, which suggests it may be patchy, full of holes, or simply not extending in every direction. We're not looking at a crisp object. We are looking at a faint smudge that might be a cloud, or might be the overlapping edges of several, or might be something subtler still. It helps to picture the whole arrangement honestly. Imagine drifting in a small boat through a wide stretch of sea where patches of mist lie scattered across the water. Some thick, some thin, some barely there. All of them slowly moving, their edges blurring into one another. You can tell you are passing from one patch into another by a change in the air, but you could never draw sharp lines on a chart to say exactly where one mist ends and the next begins. That is the space ahead of the Sun. A scattering of thin, drifting cloudlets, overlapping with no clean boundaries between them. This patchwork is why our forecast keeps coming out as ranges instead of dates, as maybes instead of certainties. To know what the Sun will meet next, and when, we would need to map these faint wisps far better than a few stellar sightlines allow. We would need to know their true shapes, their densities, their edges, and how they are moving against one another. With the tools we have had, that map has stayed frustratingly rough, so we arrive, plainly, at the admission built into our title. We can sketch the neighbourhood, but we cannot yet read it with confidence. The clouds are real, the motion is real, but the details that would let us truly understand what we are moving into remain out of reach. It is worth pausing to lay out clearly and without flinching exactly why this is so hard. It is a fair question to ask after all of this, why the experts cannot simply tell us what we are moving into. We have spacecraft beyond the heliopause, we have mapped the ribbon across the whole sky, we have measured the wind of atoms to a fraction of a mile a second. Why, with all that, is the space just ahead of us still described with words like uncertain, contested, and not well understood? The honesty of the answer is part of what makes this story worth telling. The first reason is that we are looking at the faintest stuff in the universe. The clouds around the Sun hold less than one atom in a sugar cube of space. They give off almost no light of their own. We cannot photograph them. Nearly everything we know about them comes from the indirect method we have met before, reading the dark fingerprints that the gas presses into the light of stars behind it. That works, but it is a thin thread of evidence to hang a whole map on. The second reason follows from the first. To read a cloud, you need a bright star shining through it, and you only learn about the exact line between you and that star. Toward the G-cloud, for instance, we have just a couple of useful stars, only a couple of narrow windows through the entire cloud. Imagine trying to map a whole country by peering through 2 drinking straws. You would learn something real along those 2 lines, and almost nothing about everything in between. That is genuinely the situation for some of our nearest neighbours in gas. The third reason is that the clouds will not hold still or behave. They overlap. They drift at different speeds. Their edges are ragged rather than sharp. The Local Interstellar Cloud and the G Cloud may already be touching, their boundaries smeared together so that there is no clean line to find. A wisp that looks solid toward one star may have a hole in it toward another. The neighbourhood is not a set of tidy objects waiting to be catalogued. It is a shifting, blurry patchwork. And then comes the deepest uncertainty, the one that unsettles the whole picture. Some scientists question whether these separate cloudlets are truly separate clouds at all. A competing idea holds that what we have been calling many small clouds might instead be one single, lumpy cloud surrounding the sun in every direction, with internal currents that only make it look like a patchwork when we read it along different lines of sight. In that view, the gas is being stretched and compressed by large-scale flows or old shock waves rippling through it, and our neat catalogue of cloudlets is partly a trick of perspective. When experts disagree this fundamentally about whether we are seeing many things or one thing, you know the subject is still genuinely open. This is not a failure of science. It is the front edge of it, the place where careful people freely admit what they do not yet know. The sun's nearby environment is one of the hardest things in all of astronomy to pin down, precisely because it is so close, so faint, and so empty, the very qualities that make it slip through our instruments. So we hold two things at once. We know enough to say, truthfully, that Earth is drifting out of one thin cloud, and toward others we can barely see, and we know little enough that the details remain a real and open mystery. To understand why all these clouds are here in the first place, we have to pull far back and look at the enormous near-empty cavity that holds them all. Step back now, far back, much farther than any cloud. Pull your view out until the Local Interstellar Cloud and the G Cloud and all the little cloudlets shrink to specks. When you do, a much larger structure comes into view, and it reframes everything. All of those clouds, and the sun along with them, are sitting inside an enormous, nearly empty cavity in the galaxy. Astronomers call it the local bubble. The local bubble is vast. It spans roughly 1,000 light-years across. To grasp that, remember that the Local Interstellar Cloud, which took like 30 years to cross, is just a tiny wisp adrift within it. The bubble is more than 30 times wider still. If the cloud we live in were a single room, the local bubble would be a continent. Everything we have discussed so far, every nearby cloud, every nearby star within hundreds of light-years, lies inside this one great hollow. And it is, for the most part, astonishingly empty. The gas inside the local bubble is far thinner even than the thin clouds floating within it, around one atom in 1,000 sugar cubes of space, a near-perfect void. It is also extremely hot, heated to something like 1,000,000 degrees, though once again the gas is so sparse that the heat is meaningless to anything passing through. The bubble is a great cleared-out hollow of hot, ghost-thin gas, with denser wisps like our local fluff drifting through its interior like smoke in a cathedral. The clouds, then, are not scattered randomly through the galaxy. They are the leftover scraps inside a cavity, the last bits of denser gas that survive within an otherwise swept-out hole. Picture a hole blown in a fog. The hole is mostly clear, but a few tatters of mist still hang inside it. The Local Interstellar Cloud is one of those tatters, and we are drifting through it, inside the larger hole. The shape of the bubble is stranger than the word suggests. It is not a tidy sphere. The best three-dimensional maps show it more like a long, irregular chimney, or a length of pipe, narrow in some directions and stretched open in others, punching up out of the flat plane of the Milky Way. Our galaxy is a great disk of stars and gas, and the local bubble appears to break through that disk like a vent, open toward the spaces above and below. We do not sit in a round room. We sit inside a tall, ragged shaft carved through the galactic floor. When did the sun enter this cavity? Long before it entered our current cloud. The best estimates suggest the sun rolled into the interior of the local bubble around 5 million years ago, during its endless arc around the galaxy. So for the last several million years, the whole stretch of time in which our earliest upright ancestors appeared and evolved, The solar system has been travelling through the inside of this great hollow. Before that, it lived in other environments, other gas, other neighbourhoods of the galaxy. The bubble, too, is just one chapter, a long one, in the sun's restless journey. That raises the question that turns this from a description into a story. A cavity 1,000 light-years wide, swept clean of gas and heated to 1,000,000 degrees, does not simply happen. Something tremendous must have blown it open, something powerful enough to push that much material aside across that much space. Whatever did it would have been among the most violent events the galaxy can produce. And we know what it was. The bubble was carved by dying stars by a long series of titanic explosions, and that story is written into the rocks of the Earth itself. It is where we go next. A cavity 1,000 light-years across does not carve itself. To sweep that much gas aside across that much space takes one of the most violent forces the galaxy knows, the explosion of a dying star. And the local bubble was not blown open by a single blast. It took a whole series of them, a string of stellar deaths spread over millions of years, all working in roughly the same neighbourhood. When a massive star runs out of fuel, it dies in a supernova, an explosion so bright it can briefly outshine its entire galaxy. The blast hurls the star's outer layers outward at thousands of miles a second and sends a shockwave ploughing into the surrounding gas. A single supernova clears out a sizable region around it, but if many massive stars are born close together, they tend to die close together too within a few million years of one another, and their explosions overlap. Each new blast pushes against gas already swept aside by the last, and together they hollow out something enormous. That is what happened around us. The culprits belong to a great family of young, massive stars called the Scorpius-Centaurus Association, the nearest large group of such stars to the Sun, spread across the southern sky in the directions of the constellations Scorpius and Centaurus. Within that family, two clusters in particular, known as Upper Centaurus Lupus and Lower Centaurus Crux, held many heavy stars destined for early explosive deaths, and die they did in a long cadence of supernovae. The best reconstructions suggest that something like 15 stars exploded over the past several million years to carve the local bubble we see today. The first of these blasts went off about 14 million years ago. From then on, explosion followed explosion, each one driving the growing cavity wider, sweeping the interstellar gas outward into a great expanding shell. The bubble grew the way a snowplow builds a wall, pushing the gas ahead of it into an ever larger ring while clearing the space behind. Here is the detail that brings it close to home. The series of explosions did not stop in the distant past. The most recent of them appears to have gone off only about 2 million years ago, near enough in time that our own ancestors, the early members of our human line, would have been alive on Earth to see it. A supernova that close would have blazed in the sky brighter than the full moon, bright enough to read by at night, lingering for weeks. No one wrote it down, because no one yet could write. But it happened, and as we will see, it left a mark we can still find. It is worth pausing on the sheer reach of this. The Sun played no part in making the bubble. We are simply passing through the hollow that other larger stars blew open as they died. We are living inside a graveyard, a vast cleared space carved by the deaths of stars that vanished before our species existed. The emptiness around us is not original to the galaxy. It was made violently by events with definite dates and definite causes in a part of the sky we can still point to. This is a strong claim, that a handful of specific explosions, the most recent only 2 million years ago, hollowed out the space we live in. How could we possibly know such a thing happened when no one witnessed it and the stars themselves are long gone? The answer came not from telescopes pointed at the sky, but from a single mission that mapped the positions and motions of more than 1 billion stars and let us run the whole history backward. For decades, the local bubble was a reasonable guess. Astronomers could tell from the thin hot gas around us and the absence of dense material nearby that the Sun probably sat inside some kind of cavity, but they could not see its shape, could not trace its walls, could not say with confidence how it formed or when. The bubble was an idea sketched on the edge of what the data allowed. What turned it from a guess into a map was a single patient spacecraft, and the largest census of stars ever taken. That spacecraft was Gaia, a mission of the European Space Agency, launched to do one thing with extraordinary precision: measure the exact positions, distances, and motions of more than 1 billion stars in our galaxy. Earlier star maps were flat, two-dimensional pictures, telling you where a star sat on the sky, but not how far away it was or which way it was drifting. Gaia added the missing dimensions. For each of its billion stars, it pinned down the true distance and the direction of travel, turning a flat photograph of the heavens into a living three-dimensional model you could move through and rewind. A team of astronomers, including Catherine Zucker and Alyssa Goodman, took that flood of data and asked a pointed question. They looked at the young stars and the dense star-forming clouds scattered around the Sun, within roughly 500 light-years, and they measured not just where each one was, but how it was moving. Then they did something no flat map could allow. They ran the clock backward, rewinding the motions of all those stars and clouds to see where they had been in the deep past. The result, published in the year 2022, was a revelation, and the team described the moment of seeing it as a genuine eureka. Nearly all the major star-forming regions near the Sun, it turned out, sat on the surface of a single great shell, and nearly all of them were moving outward, away from a common centre, perpendicular to that shell's surface. They were riding the skin of an expanding bubble. When the team rewound the motions all the way, the stars converged, and the bubble shrank to a point, revealing where and when it had begun. The numbers matched the supernova story exactly. A cavity inflated by a chain of explosions starting about 14 million years ago, still gently expanding today. The map also showed the bubble's true lopsided shape, the long chimney breaking through the plane of the galaxy, and it confirmed that the Sun is merely a visitor passing through the interior, not a resident of long standing. We rolled into this hollow a few million years ago, and will roll out the other side in time. One of the team members likened the galaxy to a great holy cheese, riddled with bubbles blown by dying stars, with new stars forming in the dense rims around each hole. Our bubble is simply the one we happen to live inside, the first whose full history we have been able to reconstruct. What makes this work so satisfying is that it ties the threads together. The hot thin gas around us, the clouds drifting through it, the ring of young stars on the bubble's wall, the dates of the ancient explosions, all of it now fits one coherent picture, built from the measured motion of 1 billion stars wound backward through time. But the bubble is not only a relic of past destruction, its expanding wall is doing something creative right now, out on its distant surface, something that connects the death of old stars to the birth of new ones. That is where we turn next. The local bubble is not just an empty grave left behind by dying stars. Out on its distant wall, it is doing the opposite of dying. It is making new stars. The same explosions that hollowed out the cavity also swept the surrounding gas into a great shell, and that shell, dense and cold along its rim, has become one of the most productive nurseries of new suns in our entire region of the galaxy. The reason is simple, and it follows from how the bubble grew. When a chain of supernova pushes gas outward, the gas does not vanish. It piles up at the edges, like snow heaped at the sides of a plough's path. Over millions of years, the interior is swept clean while the rim grows steadily denser, gathering more and more material into a thick, cold ring. And dense, cold gas is exactly the raw stuff from which stars are born. Squeeze enough of it together and gravity takes over, pulling the gas into clumps that collapse, heat up, and ignite as new stars. This is not a guess. When the astronomers mapped the young stars around the Sun in 3 dimensions, they found nearly all of them sitting on the surface of the local bubble, strung along its wall like beads on a wire. 7 well-known star-forming regions lie on that shell, dense clouds with names like Orion, Taurus, Ophiuchus, and Lupus, the very places where telescopes today watch fresh stars lighting up inside cocoons of gas and dust. They are not scattered at random through space. They are arranged on the skin of our bubble, because the bubble's wall is what gathered them. The most famous of these is the Orion region, home to the great nebula you can glimpse as a faint smudge in the hunter's sword on a clear winter night. Inside that nebula, stars are being born right now, condensing out of collapsing gas, some of them surrounded by disks that may one day form planets. Those newborn suns sit on the wall of the same bubble whose interior we drift through. The death of the old stars that blew the cavity is, quite directly, the cause of the birth of the new ones forming on its rim. There is a beautiful circularity in this, a kind of cosmic recycling. Massive stars are born, live fast, and die in supernovae. Those explosions sweep the surrounding gas into a dense shell. The shell collapses here and there into new stars, some of them massive enough to die as supernovae in their turn, blowing new bubbles, sweeping new shells, seeding the next generation. The galaxy renews itself this way, over and over, with each round of death sowing the seeds of the next round of birth. Our neighbourhood is one frame in that endless cycle. It is worth holding the strangeness of our position in all this. We live inside the cleared-out hollow, the quiet eye of a storm that finished long ago. The action, the creation, is happening far out on the walls, hundreds of light-years away, where the swept-up gas is busy making suns. We are surrounded, at a great distance, by a ring of stellar nurseries, all of them the children of the same explosions that made our hollow. The emptiness around us and the fertile rim far away are two faces of a single event, and the bubble is not alone. It turns out that our cavity is connected to others, joined by tunnels and shafts in a vast porous structure that riddles this whole part of the galaxy. To see how the bubbles link together, we follow the chimney upward, out of the plane of the Milky Way. Our bubble has an unusual shape, and that shape is a clue. The local bubble is not a closed, round cavern. The three-dimensional maps show it stretched into a tall, irregular shaft, narrow across the plane of the galaxy but open above and below, breaking out of the flat disk of the Milky Way like a vent in a floor. Astronomers have a name for this open shaft. They call it the local chimney. To picture it, you have to picture the galaxy honestly. The Milky Way is shaped like a vast, thin disk, a great plate of stars and gas, far wider than it is thick. The Sun sits inside that plate, roughly in its middle layer. Most of the dense gas is concentrated in the plane of the disk, the way most of the weather sits in the lower layers of Earth's atmosphere. Above and below the plane, the gas thins out quickly into a sparse halo. So when a series of supernovae blows a bubble inside the disk, the cavity finds it easiest to grow upward and downward, where there is less gas to push against. The bubble vents through the disk, opening into the thinner space above and below, like hot air escaping up a chimney. That is what the local chimney is, the open top and bottom of our bubble, where the cavity breaks through the galactic plane and connects to the sparse halo beyond. We do not live in a sealed room. We live in a shaft that is open at both ends, venting into the wider galaxy above and below the disk, and our chimney is not the only one. Branching off from the local bubble, threading through the denser gas around it, are tunnels, narrow passages that connect our cavity to other cavities nearby. These tunnels and bubbles interlock, cavity opening into tunnel opening into cavity, throughout this whole region of the galaxy. The structure is porous, riddled with holes and passages, far more open and connected than the old picture of stars floating in smooth, uniform gas. The best image for it is an old and apt one, a sponge or a block of holy cheese. The solid part is the dense interstellar gas where stars still cluster. The holes are the bubbles, blown by generations of dying stars, swept clear of gas and connected to one another by tunnels where the walls between them broke down. The Sun, right now, is drifting through one of the larger holes, with passages leading off to neighbouring holes in several directions. If this porous, sponge-like structure is typical of the galaxy as a whole, and there is good reason to think it is, then much of the Milky Way is built this way, a froth of interconnected bubbles blown by stellar death. This changes how we should think about the Sun's long journey. As it arcs around the galaxy over hundreds of millions of years, the Sun does not glide through a smooth, even medium. It travels through this froth, passing from dense regions into bubbles, through tunnels into other bubbles, in and out of clouds, the density around it rising and falling as it goes. The space around us has a texture, a structure, a geography. And that geography matters, because as we'll see, when the Sun moves from a thin region into a dense one, the consequences reach all the way down to the Earth. Before we follow that thread, there is one more step back to take. We have placed ourselves inside a cloud, inside a bubble, inside a chimney connected to other bubbles. Where does all of this sit in the galaxy as a whole? It is time to find our full address. We have been zooming out step by step, from the room of our cloud to the great hollow of the bubble, to the chimney and the tunnels that connect it to its neighbours. Now take the final step back and ask the largest version of the question. Where, in the whole sweep of the Milky Way, does all of this sit? What is our full address in the galaxy? The Milky Way is a spiral galaxy, a vast rotating disk of several 100 billion stars wound into great curving arms. Those spiral arms are the bright lanes where gas piles up and new stars blaze, the features that give spiral galaxies their pinwheel beauty when we see them from outside. Our galaxy has several major arms, sweeping out from the crowded central bulge in long trailing curves. You might expect the Sun to live in one of these grand arms. It does not quite. Instead, the Sun sits in a smaller, in-between feature, a minor spur of gas and stars wedged between two of the major arms. It is called the Orion Spur, or sometimes the Orion Arm, named for the constellation whose bright stars lie along it. It is a modest structure compared to the great arms on either side, a kind of bridge or side street rather than a main avenue. The local bubble, our cloud, the Sun, and everything we've discussed all sit within this Orion Spur. One spacecraft team described our location simply. The Sun is in a finger of the galaxy called the Orion Spur. Now set the distances in order, because the nesting is the point. The Earth orbits the Sun. The Sun sits inside the Local Interstellar Cloud, 30 light-years across. The cloud drifts inside the local bubble, 1,000 light-years across. The bubble sits within the Orion Spur, a side branch thousands of light-years long. The spur lies between two major arms of the Milky Way, a disk 100,000 light-years wide, and the whole galaxy is one of countless galaxies in a universe whose edge we cannot see. We live at the bottom of a deep stack of nested homes, each one vast, each one floating inside something vaster, and remember that none of it is still. The Sun carries us around the galaxy on that great arc, the one that takes more than 200 million years to complete. As it travels, it bobs gently up and down through the plane of the disk, and it drifts slowly in and out of the spiral features. The Orion Spur is our neighbourhood for now, but over tens of millions of years even that will change. The address is not permanent. It is a snapshot of where the current has carried us at this particular moment in a journey with no fixed destination. There is a quiet humility in seeing the full picture laid out. Everything that has ever mattered to any human being has happened at the bottom of this stack, on one small planet, circling one ordinary star, in a thin cloud, in a great hollow, in a minor spur, in one galaxy among billions. And yet, from that small place, we have managed to map the whole arrangement, to measure the bubble and date the explosions and chart the clouds. That is no small thing. We have now built the full picture in space, from the Earth outward to the galaxy. It is time to turn from where we are to what it does to us, and for that we must come back down, all the way down, to the rocks and ice of the Earth, where the evidence of these cosmic crossings lies waiting to be read. We have travelled outward to the edge of the galaxy and back. Now comes the turn that makes this more than a tour. Everything we have described, the clouds, the bubble, the explosions that carved it, has left a physical trace here on Earth, in the ground beneath our feet and the ice at the poles. We can hold the evidence of a nearby supernova in our hands. The fingerprint has a name. It is a rare form of iron called iron-60. To understand why iron-60 matters so much, you have to know one unusual thing about it. It is radioactive, and it does not last. Iron-60 is unstable. Over time, it decays away into other elements. The rate of that decay is steady and known. In about 2.5 million years, half of any batch of iron-60 will have vanished. After several such spans, essentially none is left. This is what scientists call a half-life, and the half-life of iron-60 is the key to the whole story. Here is why. The Earth is 4.5 billion years old. If any iron-60 had been present when the planet formed, it would have decayed away completely long ago, thousands of times over. There should be none left from Earth's birth, and iron-60 is not made by any ordinary process on Earth. Our planet has no way to manufacture it. So if we find iron-60 in the ground today, fresh enough to still be detectable, it cannot be left over from the Earth's formation, and it cannot have been made here. It must have arrived recently in cosmic terms from somewhere else, and there is only one place it comes from. Iron-60 is forged in the hearts of massive stars, cooked up in the final stages of their lives, and then flung out across space when those stars die in supernovae. It is, quite literally, the ash of stellar explosions. So a grain of iron-60 found on Earth is a messenger with an unmistakable return address. It says, a massive star exploded not too long ago and not too far away, close enough that some of its debris drifted across space and settled onto our world. This is what makes iron-60 such a powerful tool. It is a clock and a tracer at once. Because we know its half-life, the amount we find tells us roughly when it arrived. Because we know its only source, its presence tells us a supernova went off nearby. Where ordinary detective work fails, because the explosion left no other record and the guilty star is long gone, this single radioactive isotope testifies. It is a fingerprint left at the scene of a crime committed millions of years ago, and it has not yet faded. The amounts involved are almost unimaginably small. We are not talking about layers of iron you could see or weigh in any ordinary way. We are talking about a scattering of individual atoms, so few that detecting them at all required machines of extraordinary sensitivity and years of careful work to rule out every other possible source. But the atoms are there. They have been found more than once in more than one place, and counting them has let scientists reconstruct events no one ever witnessed. So we have a fingerprint, and we know what it means. The next question is what it tells us. When we look for iron-60 in the Earth, we do not find it spread evenly. We find it concentrated in distinct pulses, layers laid down at particular moments in the deep past. Those pulses are the record of specific encounters, and reading them is where we go next. When scientists go looking for iron-60 in the Earth's deep records, they do not find it smeared evenly through time. They find it in pulses, distinct bursts concentrated at particular moments in the past, with quiet stretches in between. The Earth's archives show that our planet was dusted with this stellar ash, not once but in clear episodes, like fingerprints left on 2 separate occasions. Reading the timing of those pulses is how we connect the rocks beneath us to the explosions that carved our bubble. The strongest, clearest pulse falls in the window of roughly 2 to 3 million years ago. This is the big one, the signal that first convinced scientists that a supernova had gone off in our cosmic neighbourhood within the span of recent geological time. The amount of iron-60 laid down then stands well above the background, marking a period when debris from a nearby explosion was settling onto the Earth in measurable quantities. And that timing should sound familiar. It lines up closely with the most recent of the supernovae thought to have helped shape the local bubble, the blast estimated to have gone off about 2 million years ago. The rocks and the star maps tell the same story, from completely different directions. There is a second pulse, older and a little fainter, in the window of about 6 to 7 million years ago. This earlier signal points to another nearby explosion, or perhaps to the solar system passing through debris left by an earlier round of stellar death. Two pulses then, separated by millions of years, each marking a time when our world was exposed to fresh supernova ash. The neighbourhood was not blasted once and left alone. It was dusted repeatedly as the chain of explosions that built the bubble went off one after another over millions of years. What do these pulses actually represent? There are two ways the iron could have reached us, and they are not mutually exclusive. One is the direct blast. A supernova goes off close enough that its expanding cloud of debris eventually washes over the solar system, raining a trace of iron-60 onto the Earth. The other is slower and quieter. The solar system, on its journey, drifts into a region of space already seeded with iron-60 from an old explosion, and picks up the ash as it passes through. Both can leave the same kind of signal. Distinguishing between them and matching each pulse to a specific event is painstaking work still underway. It helps to feel the timescale in human terms. 2 to 3 million years ago, the most recent pulse is not the age of dinosaurs or some unimaginably remote epoch. It is the time of our own early ancestors, the era when upright, tool-using members of the human family were walking the plains of Africa. They lived under skies that, for a time, held an extra brilliant star, the nearby supernova blazing as it died. And in the same era, unknown to them, a thin fall of stellar iron was settling onto the Earth, into the mud of the ocean floors, where it would wait, slowly decaying, for our instruments to find it millions of years later. That is the remarkable thing about these pulses. They are not abstractions. They are specific events with specific dates, recorded in the physical substance of our planet, lining up with explosions we can place in the sky. But to read them, scientists first had to find them, and finding a scattering of individual atoms laid down millions of years ago is its own extraordinary story. Where exactly is this stellar ash hiding? That is where we turn next. A fall of stellar iron drifting onto the Earth over thousands of years does not pile up in any obvious place. There is no glittering layer, no vein you could mine. The iron-60 arrives as a faint scattering of individual atoms, mixed into everything else settling onto the planet, and then it is buried, slowly, under the steady accumulation of ordinary material. To find it, scientists had to think carefully about where such a faint ancient signal could be preserved undisturbed, and then go and dig it out, atom by atom. They found it in 3 remarkable places. The first is the floor of the deep ocean. On the seabed, far from rivers and currents, certain rocky crusts grow with extraordinary slowness, building up layer by layer over millions of years as minerals settle out of the water. A crust like this is a kind of tape recorder, running at the slowest imaginable speed, with each thin layer holding a record of what was falling onto the Earth at that time. By slicing such a crust and measuring the iron-60 in each layer, scientists could read the history of stellar ash going back millions of years, and there they found the pulses, locked in the depths of the Pacific seabed. These deep-sea crusts were where the supernova signal was first clearly detected, the discovery that launched the whole field. The second place is even more surprising: the Moon. Our companion world has no air, no water, no weather to scatter and erase a faint signal. Whatever falls onto the lunar surface tends to stay where it lands. When the Apollo missions brought back samples of lunar soil, scientists later examined them and found iron-60 there too, in amounts consistent with the same nearby supernovae. The Moon, it turns out, caught the same stellar rain we did, and held onto it as a quiet witness, confirming that the signal was real and not some quirk of the Earth's own chemistry. The third place is the ice. At the poles, snow falls and never melts, building up year after year into deep sheets of ancient ice. Like the deep-sea crusts, polar ice is a slow recorder, each layer trapping a sample of what was settling out of the sky when it fell. Scientists drilling into Antarctic ice have found iron 60 in it as well, along with other traces of supernova debris. The ice extends the record into more recent times than the slow-growing crusts can easily resolve, and as we will see, what it shows about the recent past is the most unsettling part of the whole story. Across all three archives, the seabed, the moon, and the ice, the same signal appears, and that agreement is what makes it trustworthy. A single detection in one place might be doubted, blamed on contamination or some unknown local process, but the same rare isotope, in the same amounts, in the same time windows, found in the deep Pacific, in lunar soil, and in polar ice, is very hard to explain away. Three independent witnesses, in three utterly different settings, all telling the same story of nearby stellar death. It is worth pausing on the sheer difficulty of this work. We are talking about counting individual atoms of a substance present in vanishingly small amounts, sorting them out from the overwhelming background of ordinary matter, and doing it with enough confidence to date events millions of years old. It took machines of exquisite sensitivity, and researchers willing to spend years chasing a whisper of a signal. That they succeeded at all is one of the quiet marvels of modern science. So the ancient pulses are well established, recorded in three places, matched to explosions in the sky. But the ice held one more surprise, a signal not from millions of years ago, but from almost yesterday. And that is where the story takes its strangest turn. The ancient pulses were astonishing enough. Proof that supernova went off near us millions of years ago, written into the seabed and the moon and the ice. But then scientists looked at the most recent records, the freshest snow, the youngest layers, expecting to find nothing. The ancient explosions were long over. Any iron 60 they delivered should have finished falling ages ago. The recent record should have been blank. It was not. In Antarctic surface snow less than 20 years old, snow that fell within living memory, scientists found iron 60. Not a great deal of it, but unmistakably there, the same rare stellar isotope, in snow so young it was falling while many of us were already alive. This was deeply strange. Iron 60 cannot be made on Earth. Its only source is a supernova, and there has been no nearby supernova in recent times, nothing in the last few million years close enough to explain fresh ash arriving today. So where was it coming from? The discovery raised a sharp and simple question. If no star has exploded near us recently, why is stellar iron still settling onto the Earth right now? The atoms in that fresh snow had to have been forged in some ancient explosion, yet they were arriving in the present day. Something was delivering old supernova ash to us continuously, long after the explosions that made it had ended. The leading answer ties the whole story together, and it brings us right back to the cloud we live in. The idea is this: the local interstellar cloud, the thin wisp the sun is currently drifting through, is itself laced with iron 60, seeded with the ash of an old supernova and holding on to it. The isotope, with its long half-life, can survive in the cloud for a very long time, far longer than the few thousand years we have been passing through. So as the solar system moves through the local interstellar cloud, the Earth is sweeping up a faint, steady drizzle of this stored stellar dust. The iron in our fresh snow is not from a recent blast. It is from an old one, carried to us by the very cloud we happen to be inside. If that is right, the implication is quietly profound. It means the fresh iron 60 is direct, physical evidence that we are, right now, moving through a cloud of supernova debris. Not millions of years ago, today. Every year, as the Earth circles the Sun within the local interstellar cloud, it gathers a few more atoms of stardust forged in a star that died long before the cloud reached us. The snow falling on Antarctica this winter may carry, mixed into it, the ash of an explosion older than our species. It must be said clearly to keep the wonder honest. The amounts are tiny, and they pose no danger of any kind. This is not a hazard to anyone or anything. The iron arrives as a scattering of individual atoms, far too few to affect health or climate or daily life. Its importance is not as a threat, but as a message. It is a tracer, a faint signal that lets us confirm by holding the evidence in fresh snow that the cloud around us is a piece of an exploded star. This was a striking idea, but for years it remained a hypothesis, hard to prove. To confirm it, scientists needed to show that the iron 60 in the ice tracked the cloud itself, rising and falling with our passage through it. That confirmation came only very recently, from a careful study of ancient Antarctic ice, and it is the freshest chapter in this entire story. The idea that the local interstellar cloud is itself laced with supernova iron was elegant, but for years it lacked the final proof. Finding iron 60 in fresh snow showed that something was delivering stellar ash to us now. It did not by itself prove that the cloud was the source. To nail that down, scientists needed to show that the amount of iron 60 reaching Earth changed as we moved into the cloud, that the signal tracked our passage through it. That proof arrived only very recently, in the year 2026, from a study led by researchers at a German laboratory, Dominic Koll and Anton Wallner among them. Their approach was clever. Earlier work had measured iron 60 in recent snow and in deep-sea sediments going back a few tens of thousands of years. This new team went after older ice, samples from an Antarctic core reaching back between 40,000 and 80,000 years, into the very period when the solar system is thought to have entered the local interstellar cloud. If the cloud was the source of the iron, then ice from before we entered the cloud should hold less of it, and ice from after our entry should hold more. The signal should switch on as we crossed into the cloud. That is close to what they found. Comparing the older ice with the more recent records, they saw that the amount of iron 60 reaching Earth was lower in the more distant past, and changed as the solar system moved into the denser cloud material. The influx was not constant. It varied in step with our passage. This was the missing link. It showed that the iron 60 is tied to the cloud itself, switching on and shifting as we move through its structure. The local interstellar cloud, the team concluded, is the likely reservoir, a body of gas seeded with the ash of an ancient stellar explosion, which the Earth has been sampling as it drifts inside. The significance reaches beyond the iron. If the cloud carries the debris of a supernova, then the cloud itself is connected to a stellar explosion. It is, in part, made of the stuff of a dead star, and that gives us, for the first time, a handle on where these nearby clouds came from. The wisps drifting through the local bubble may be the scattered, lingering remains of the same kind of explosions that blew the bubble open, the cool fragments left behind in the Great Hollow. The cloud around us is not just a random patch of gas, it is a relic, traceable to a particular kind of violent origin. There is something else this study quietly gives us, almost as valuable as the answer itself. It turns the Earth's ice into a recording instrument for our galactic journey. If the amount of iron 60 in the ice tracks our movement through the cloud, then by reading deeper and older layers we can, in principle, map the structure of the cloud we're passing through, its density rising and falling, its edges, its internal lumps, all written into the frozen archive at the poles. The ice becomes a logbook of the solar system's voyage through the local galaxy, and we have only just begun to read it. The researchers are already planning to study even older ice, from before we entered the cloud, to capture the moment of entry itself. It is a fitting place for the evidence to lead us. We began with abstract clouds and distant explosions mapped from starlight and spacecraft. We end with frozen water at the bottom of the world, holding a faint record of stardust, confirming that we are passing through the remains of a star that died long ago. The cosmic and the earthly meet in a column of Antarctic ice. But all of this evidence, the iron, the pulses, the cloud full of ash, points toward a larger and more serious question. the iron arriving today is harmless. But the same record shows that the conditions around us change as we travel, and that change can do more than deliver a sprinkle of atoms. It can squeeze our shelter. To understand what that means, we have to return to the heliosphere and ask what happens when the cloud outside grows thick. Throughout this story, our shelter has been a constant, the great bubble of the heliosphere, holding the galaxy at bay, keeping the Earth deep inside its protection. But that shelter is not guaranteed. Recall the balance that sets its size. The solar wind pushes out, the surrounding gas pushes in. The wall forms where the two pressures meet. That balance depends entirely on how thick the gas outside happens to be. And the gas outside is not always as thin as it is today. This is the idea that gives our title its weight. The clouds we have been mapping are not all the same density. The one we're in now is gossamer thin, only a few tenths of an atom in a sugar cube of space, and against such a wisp the solar wind holds the wall far out past the planets with ease. But denser clouds exist, and on its long journey the sun can wander into one. When it does, the extra pressure presses the wall inward. The shelter shrinks. The thicker the cloud, the smaller the bubble, and there is no rule that says the bubble must always stay larger than the Earth's orbit. Scientists have a stark word for the extreme version of this. They call it being descreened. The screen is the heliosphere, the shield that normally filters the harshest of the interstellar environment before it can reach the planets. To be descreened means the shield has been pushed back so far that a planet finds itself outside it, exposed directly to the raw interstellar medium, no longer wrapped in the sun's protective bubble. For that to happen to the Earth, the heliosphere would have to be compressed from its present span of well over 100 times the Earth-Sun distance down to less than 1. The cloud would have to be dense indeed. Such clouds exist. We have already met their cold, dense cousins, the dense clouds that string through parts of the galaxy, thousands of times thicker than the wisp we float in now. If the sun were to pass through one of those, the consequences for the heliosphere would be dramatic. And here is the part that turns a hypothetical into history. By tracing the sun's path backward along its galactic arc and mapping where the dense clouds have been, scientists have found that the solar system may have done exactly this in the past, ploughing into a dense cold cloud and having its shelter crushed inward. The proposed encounter fits with the iron record we've just examined. A passage through a dense, supernova-seeded cloud a couple of million years ago could deliver a strong pulse of iron 60 to the Earth, precisely because a compressed, descreened heliosphere would let interstellar material reach us far more freely than it can today. The same event that squeezed the shield could explain the stellar ash in the rocks. Two separate lines of evidence, the compression and the iron pulse, point to the same moment. It must be stressed that this is a frontier, not a settled fact. The reconstruction depends on tracing the sun's path and the cloud's paths backward over millions of years, which is difficult and uncertain work, and the exact details are debated. But the basic logic is sound and sobering. Our shelter's size is set by the world outside. The outside changes as we travel, and there have likely been times when the shelter was squeezed to a fraction of its present size, leaving the Earth far more exposed than it is today. To understand just how dramatic that squeezing could be, and what it would have done to the layout of the solar system, we turn to the detailed models of the heliosphere built by one scientist in particular, whose work has reshaped how we picture our bubble in the first place. To picture what a dense cloud would actually do to our shelter, we need the work of Opher, a space physicist who has spent her career building detailed computer models of the heliosphere. Her models have reshaped how scientists picture the bubble we live in, including the surprising claim, which stirred up real debate in her field, that the heliosphere may be shaped less like a sphere and more like a soft, deflated croissant. When such a person turns her models toward the question of dense cloud crossings, the results are worth attending to. Working with colleagues including Loeb and Loeb Peek, Opher traced the sun's path backward through the galaxy and identified a likely culprit for a past encounter. It is a dense, cold cloud lying at the end of a long string of such clouds, a structure they named the local ribbon of cold clouds, with the particular cloud at its tip called the local links of cold clouds. Their reconstruction suggested that the solar system passed through this dense cloud roughly 2 to 3 million years ago, the same window as the strongest iron pulse in the Earth's rocks. Then they asked their models what such a passage would do. The answer was stark. This cold cloud was dense enough, thousands of times denser than the wisp we float in now, that as the solar system pushed into it, the pressure from outside overwhelmed the solar wind and crushed the heliosphere inward dramatically. In their simulations, the shelter that today reaches far past the outermost planets was squeezed down until its inner boundary lay closer to the Sun than the Earth's own orbit. The bubble shrank smaller than the ground we stand on travels in a year. Sit with what that means for the layout of the solar system. Today, every planet rides comfortably deep inside the heliosphere. In the compressed scenario, the bubble would have shrunk so far that the Earth and the other planets would have spent at least part of their orbits outside the shelter entirely, out in the raw interstellar medium, directly exposed to the dense cloud and everything it carried. As one description put it, the cloud briefly placed the Earth and the other planets outside the heliosphere's influence. The shield did not just shrink. For a time, it may have left us behind. This is the quantitative heart of the discreening idea, and Opher's team described their work as the first to show, with real numbers from a physical model, that such an encounter between the Sun and something outside the solar system could have reached all the way down to affect the Earth. It connects the grand scale, the Sun's wandering path through clouds, to the intimate scale, the conditions at our own planet, through the physics of a squeezed bubble. As Opher put it, stars move, and now we see that as they move, they can encounter drastic changes in their surroundings. The honest caveats remain firmly in place. The sizes of these ancient clouds, the exact path of the Sun, and the precise degree of compression are all uncertain, reconstructed across millions of years from limited data, and other scientists weigh the details differently. But the work shows, with concrete modelling, that a dense cloud crossing is not just a vague worry. It is a specific physical scenario with calculable consequences, and the consequences are large. If the Earth were exposed like that, even briefly, what would actually reach us? The cloud's gas and dust, yes, and the stellar iron we have already traced. But there is something else, something the heliosphere normally holds back, that would come flooding in when the shield shrank. To understand the real consequences for our planet, we have to talk about cosmic rays. When we talk about the heliosphere protecting the Earth, we should be precise about what it protects us from. The thin gas of an interstellar cloud is not in itself very threatening. It is far too sparse to harm anything. The more important thing the shelter holds back is faster and more dangerous, a steady sleet of high-energy particles racing through the galaxy at nearly the speed of light. These are the cosmic rays, and they are where the consequences of a shrunken shield become real. Cosmic rays are not rays of light at all despite the name. They are particles, mostly the bare cores of atoms, stripped down and flung across space at tremendous speed. Many of them are born in supernovae, the same explosions that built our bubble, which act as enormous natural accelerators, hurling particles outward with staggering energy. These particles then wander the galaxy for ages, spiraling along magnetic fields, filling interstellar space with a constant, fast-moving sleet. They come from every direction, all the time. The heliosphere is our first line of defense against them. As galactic cosmic rays try to penetrate our bubble, they run into the outflowing solar wind and its tangled magnetic field, which deflect and slow them, turning many aside before they ever reach the inner planets. The shield is not perfect. Some always get through, and we will return to those. But it cuts the incoming flood substantially. The deeper and stronger the heliosphere, the more cosmic rays it turns away. This is why the size of the bubble matters so much, and why a compressed bubble is more than a curiosity. Now connect this to the disc screening scenario. If a dense cloud crushed the heliosphere down inside the Earth's orbit, then for that period the Earth would have lost much of its cosmic ray shielding. The galactic sleet that is normally deflected far out in the bubble would have reached the Earth far more freely, raising the dose of high-energy particles striking the top of the atmosphere. The exposure that the shelter normally spreads thin would have come in thick. A planet that spends part of its year outside a shrunken bubble is a planet bathed in more radiation from the galaxy than it is used to. What does an increase in cosmic rays actually do? At the Earth's surface, we are protected by a second shield, our own thick atmosphere and the planet's magnetic field, which together absorb and deflect most of what gets past the heliosphere. So a rise in cosmic rays during a cloud crossing would not be a death ray sweeping the surface. Its effects would be subtler. Cosmic rays striking the upper atmosphere set off cascades of reactions, producing showers of secondary particles and altering the chemistry high above us. They also create certain rare isotopes in the air, atoms that then settle to the ground and, like iron-60, become a record we can read. One such isotope, a form of beryllium, is being studied for exactly this purpose, as another possible tracer of past cloud crossings preserved in the Earth's archives. The picture, then, is of a planet whose exposure to the galaxy waxes and wanes as the sun journeys through regions of different density, with the heliosphere swelling and shrinking in response, and the cosmic ray dose rising and falling to match. For most of the time, including now, the shelter is large and the dose is low. But during a dense cloud crossing, the balance tips, and more of the galaxy's radiation reaches our air, which leads to the question that has drawn the most attention and demands the most care. If a cloud crossing changes the chemistry of the upper atmosphere and lets in more radiation, could it reach all the way down to the climate, to the weather, to the conditions for life itself? Here we must walk slowly because this is where solid evidence thins out and speculation begins. We come now to the most tempting question in this whole story, and the one that demands the most discipline. If the sun's passage through a dense cloud can shrink our shelter and let more radiation reach the upper air, could it have reached further still, down into the climate, leaving a mark on the very weather of the ancient Earth? It is a thrilling idea. It is also one where the honest answer is a careful maybe, and we must not let the thrill outrun the evidence. Start with what is genuinely suggestive. The strongest pulse of supernova iron in the Earth's rocks falls around 2 to 3 million years ago. That same stretch of time, in the Earth's climate record, was a period of cooling, part of the long slide toward the ice ages that gripped the planet in the epoch that followed. The timing of the iron and the timing of the cooling overlap. To a curious mind, that overlap is electric. Did the cloud crossing, the shrunken shield, the extra radiation somehow help tip the climate toward cold? There are real physical pathways one can sketch. More cosmic rays reaching the atmosphere could, in principle, affect the chemistry of the upper air, including the ozone that shields the surface and the fine particles around which clouds form. Some researchers have proposed that changes in high-altitude chemistry, or in cloud formation, driven by a rise in cosmic radiation, could nudge the climate. Others have suggested that dust from a dense cloud, reaching the inner solar system when the shield was down, might have dimmed sunlight slightly. The recent modelling work explicitly framed itself as the first to show, with numbers, that such an encounter could have affected the Earth's climate. The mechanisms are not absurd. They are plausible enough to take seriously, but now the discipline. Plausible is not proven, and overlap in timing is not the same as cause. The Earth's climate is driven by many powerful forces working together: the slow wobbles and tilts of our orbit, the slow drift of continents, the rise and fall of carbon dioxide in the air, the patterns of the great ocean currents. These are the heavy machinery of climate change, well established and well measured. Against them, the effect of a cloud crossing, if it exists at all, would be one small influence among many, and it is genuinely difficult to disentangle. The cooling 2 to 3 million years ago has explanations that owe nothing to interstellar clouds. The cloud crossing may have contributed a nudge, or it may have been a coincidence riding alongside the real causes. This is the kind of place where good science holds two thoughts at once without forcing a conclusion. The iron is real, the cooling is real, the overlap is real, and the link between them remains unproven, a live hypothesis under investigation, not a settled fact. The researchers themselves are careful here. They have shown that an effect is possible and worth pursuing, not that it certainly happened. To claim more than that would be to trade honest wonder for a tidy story, and the honest version is more interesting anyway, because it sits right at the edge of what we know. So we let it rest there, calmly. It may be that in the deep past, the wandering of the sun through the clouds of the galaxy left a faint fingerprint on the climate of the Earth, a subtle pressure toward cold during the ages when our ancestors were finding their feet. Or it may be that the cosmos and the climate simply kept their own separate clocks, which happened to chime together. We do not yet know which. What we can say is that the question is real, the evidence is being gathered, and the answer, when it comes, will be earned slowly. If the climate connection is uncertain, there is an even more delicate question waiting behind it, one that touches us more directly than weather. What might all of this have meant for living things, including the long line of life that leads to us? Behind every question about climate and radiation lies a more intimate one, the one we cannot help but ask. What might all of this have meant for life? The sun has wandered through clouds, the shield has shrunk, extra radiation has reached the air, stellar iron has fallen onto the Earth, all during the very stretch of time in which our own ancestors were evolving. It is natural to wonder whether the galaxy reached down and touched the story of life itself. Here, more than anywhere, we must be both open and honest. Begin with reassurance, because it is warranted. The iron 60 falling on us today from the cloud we currently inhabit is utterly harmless, a scattering of individual atoms far too sparse to affect any living thing. And even in the dramatic pass crossings, life on Earth was never naked to the galaxy. Our planet carries its own defences that have nothing to do with the heliosphere, a thick atmosphere and a strong magnetic field that together absorb and deflect the great majority of cosmic radiation before it can reach the surface. Even with the heliosphere compressed, these inner shields remained on duty. Life was never going to be sterilized by a cloud crossing, so if there was an effect on living things, it would have been subtle, not catastrophic. Researchers have raised the possibility that a sustained rise in radiation reaching the surface could, over long periods, nudge the rate at which mutations occur in living cells, or that the climate shifts associated with a crossing could reshape the environments that creatures had to adapt to. Some have speculated about links between ancient cosmic events and turning points in the history of life. These are intriguing threads, but they are threads, not ropes. The evidence connecting any specific cloud crossing to any specific change in living things is thin, and it should be treated with even more caution than the climate question. The temptation here is powerful and worth naming so we can resist it. It is deeply appealing to imagine that the rise of our own ancestors was somehow written in the stars, triggered by a nearby supernova or a passage through a cloud. It makes a tidy and flattering story, the cosmos conspiring to produce us. But the actual record of human evolution is explained, as far as we can tell, by earthly forces, changing climates driven by ordinary causes, shifting landscapes, the slow pressures of competition and adaptation. There is no good evidence that a cloud crossing made us, and to claim otherwise would be to mistake a beautiful coincidence for a cause. What we can say, calmly and truthfully, is something gentler and still remarkable. Life on Earth has unfolded inside a moving environment. The space around our planet has not been a fixed, unchanging void. It has shifted as the sun has travelled, sometimes thin and quiet, sometimes thicker and more exposed. Whatever the precise effects, life has been living this whole time aboard a vessel passing through changing waters. The conditions just beyond our sky have been part of the backdrop against which every creature that ever lived played out its existence, even if that backdrop touched them only lightly or not at all. That is enough to hold in wonder without overclaiming. We are creatures of a planet that drifts through a structured, changing galaxy, and our long history has run its course inside that drift. Whether the galaxy left fingerprints on us, or merely formed the silent setting of our story, it has been present the entire way, closer and more active than anyone suspected until very recently. And the drift is not over. We are, as we have seen, near the edge of our current cloud, with others ahead. So it is fair to turn from the past to the future and ask what the coming stretch of the journey holds, and how soon the scenery will change again. We have spent much of this journey looking backward, reading the past in iron and ice, reconstructing crossings that happened millions of years ago. But the sun is still moving, still carrying us forward along its arc, and the road ahead is just as real as the road behind. So it is fair to ask, with the same calm care, what comes next? Where does the current take us from here? The nearest certainty is that we will leave the cloud we're in. The solar system sits near the edge of the Local Interstellar Cloud, and within a span of a few thousand years, perhaps as little as 2,000, we will drift out of it entirely. By the long clock of the galaxy, this is imminent, the next bend in the river already in sight. When we cross that boundary, the faint wind of atoms in our face will change, the gas around our shelter will shift, and the conditions at the edge of the heliosphere will be rewritten, gently, into a new configuration. Beyond that edge, the picture grows softer, as we have come to expect from this contested neighbourhood. The next environment may be the G-cloud, the cooler, possibly denser wisp that holds our nearest stellar neighbours, or it may be one of the smaller cloudlets crowding the space ahead, like the faint apex cloud lying in our direction of travel. Or the boundaries may be so blurred, the clouds so overlapping, that we will pass from one into the next with no clear threshold at all, a slow fading rather than a crossing. We cannot yet say which, because as we have seen plainly, the map of what lies ahead is exactly the part we understand least. What we can say is that none of the clouds known to lie immediately ahead are dense enough to threaten the kind of dramatic compression the sun endured in the deep past. The G-cloud may press a little harder on our shelter than the current wisp does, perhaps shrinking the bubble somewhat and letting in a little more radiation, but it is still a thin, warm cloud, nothing like the dense, cold clouds that crushed the heliosphere millions of years ago. The next stretch of road, as far as we can see it, looks gentle. The shelter will flex, the conditions will shift, but the Earth will remain wrapped in its protective bubble. Further out over millions of years, the deeper uncertainty returns, and so does the possibility of more dramatic encounters. As the sun continues its great arc around the galaxy, bobbing through the disk, threading through the froth of bubbles and tunnels, it will eventually wander into new regions, some thin, some perhaps dense. Whether and when it might meet another dense cloud, the kind that could squeeze the shield hard, is not something we can predict in detail. It depends on the geography of the galaxy along a path stretching millions of years into the future, a path we can only sketch in the roughest terms. So the honest forecast is layered, like the journey itself. In the near term, a few thousand years, we leave our cloud for another, with little drama expected. In the medium term, the identity of the next cloud is genuinely uncertain, the frontier of current research. In the long term, over millions of years, the sun will surely pass through more varied terrain, with the real but unpredictable possibility of denser encounters far down the road. We are not heading toward a known destination. We are drifting, as we always have, into territory we can only partly see. That partial seeing is not a reason for unease, it is an invitation. For the first time in history, we have the tools to start mapping the road ahead, to turn the blurry frontier into something clearer. A new generation of spacecraft is being launched and aimed outward, built to study the very boundary we have been circling this whole time. What they may show us is where we turn next. For all that we have learned, the honest refrain of this story has been how much remains uncertain, especially about the space just ahead of us. But that uncertainty is not permanent. It reflects the limits of the tools we have had, and those tools are being replaced and added to right now. A new generation of spacecraft is turning its attention outward, to the very boundary we have spent this whole journey exploring, and the coming years promise to sharpen the blurry map considerably. The freshest of these new eyes launched in the year 2025. It is called the Interstellar Mapping and Acceleration Probe, and its purpose is written in its name: to map the interaction between our shelter and the interstellar medium with far greater clarity than ever before. It builds directly on the work of the spacecraft that discovered the ribbon, gathering the faint atoms streaming back from the boundary, but with sharper instruments and a fuller view. Where the earlier mission gave us our first surprising glimpse of the edge, this new probe is designed to study it in detail, to watch how the boundary shifts, and to read more precisely the properties of the cloud pressing in from outside. It arrived just as the Sun's nearby environment became one of the liveliest questions in the field. Then there are the old travellers, still working far beyond the wall. Voyager 1 and Voyager 2 continue to drift outward through interstellar space, their instruments still returning data across the immense gulf, growing fainter each year as their power slowly fails. They remain our only direct samples of the region beyond the heliopause, and scientists watch them closely for the moment when they finally pass into truly pristine interstellar space, beyond the distorting influence of our own bubble. Every year they survive, they push our reach a little farther into the unknown. A third craft is on its way to join them, though it will take time. New Horizons, the spacecraft that gave us our first close look at Pluto and then flew on past an even more distant icy world, is still heading outward, bound eventually for the edge of the heliosphere. If its instruments are still working when it arrives, perhaps a decade or so from now, it will become the third human-made object to cross into interstellar space, carrying a fresh set of eyes to a boundary we have so far touched in only 2 places. A third crossing, in a third direction, would tell us much about how the wall varies around us. Taken together, these missions represent something hopeful. For most of human history, the space beyond our sky was pure mystery, not even known to have structure. Within a single lifetime, we have gone from suspecting a bubble to mapping it, from guessing at the clouds to weighing the iron they carry, from imagining the edge to sending machines across it. And now, we are building better instruments still, aimed precisely at the questions this story has left open. What cloud comes next? How the shield is changing? What the boundary truly looks like from more than 2 narrow points? The frontier we have called poorly understood is, in other words, a frontier under active exploration, with new tools arriving as we speak. The answers will come slowly, earned measurement by measurement, the way all real knowledge of this faint and distant region has been earned. But they will come. The map of where Earth is going will grow clearer in the years ahead, drawn by spacecraft built for exactly that purpose. And so we come nearly to the end of our long look outward. We have travelled from the stillness you feel in your chair to the edge of the galaxy and back, through clouds and bubbles and ancient explosions, and into the rocks and ice that hold the record of it all. It is time to return, gently, to where we began. We started in stillness. You, sitting somewhere quiet, feeling the floor steady beneath you, the world at rest. And we have spent this whole long journey learning how thoroughly that stillness is an illusion. You are moving, always, carried by the Earth around the Sun, by the Sun around the galaxy, through clouds and cavities and the scattered ash of dead stars, at speeds and across distances that the body cannot feel and the mind can barely hold. The quiet you feel is real as a sensation and false as a fact. We are, all of us, in motion. Come back now to the cloud. Right now, as you breathe, the solar system is drifting through the local interstellar cloud, a thin, warm wisp 30 light-years across, which we entered while our ancestors were painting the walls of caves, and which we will leave again within a few thousand years. The cloud is laced with the iron of an ancient exploded star, and a faint drizzle of that stardust is settling onto the Earth even tonight, into the snow at the poles, harmless and almost unimaginably sparse, a quiet message from a star that died before our kind existed. We're passing through the remains of a supernova, and we have only just learned to read the traces it leaves. Around that cloud lies the great hollow of the local bubble, blown open by a chain of stellar deaths beginning 14 million years ago, its distant walls still busy making new suns. Around that lies the Orion Spur and the wheeling disk of the Milky Way and the unmeasured dark beyond. We sit at the bottom of that great nested stack of homes, on one small world, having somehow from this single quiet vantage mapped the whole arrangement, dated the explosions, weighed the iron, and begun to chart the road ahead. And the central wonder, the one this whole journey has been circling, is simply this. The space around our planet is not a fixed and empty void. It is a place, with structure and weather and history, and we are travelling through it. The conditions just beyond our sky have shifted as the sun has wandered, thin and quiet now, thicker and more exposed in the deep past, and they will shift again as we drift on into clouds we can only partly see. Everything that has ever happened on Earth, every life, every story, has unfolded aboard this vessel, sailing through changing waters, mostly unaware that the waters were changing at all. That is why the title of this journey is honest. Earth truly is moving through regions of space we do not fully understand, near the edge of one cloud, approaching others we can barely map, with new instruments only now turning to see them clearly. The not understanding is not a failure. It is the live edge of a question we have only just become able to ask, and the answers are arriving slowly, in iron and ice, and the faint return of atoms from the wall of our shelter. If this slow look outward has stayed with you, and you would like more nights spent exploring the quiet machinery of the cosmos this way, you are warmly invited to subscribe and travel a little further with us next time. So let the stillness return. Settle back into the steady floor, the resting cup, the quiet room. None of it is truly still, and that is the gift. You are riding the slow current of the galaxy, through the ash of old stars beneath a shield older than your species, toward a horizon no one has yet mapped. The drift goes on, as it always has, carrying you gently forward through the dark, and now, at least, you know which way you're going.